Hello, and welcome back to another calculus video on optimization. This is a kind of a continuation to my last optimization video. The concepts in this video are going to be similar to the ones we've explored in the last video, and our goal is the same. We want to optimize a certain quantity. We want to minimize or maximize it, which means we have to take the information we're given and make changes, make small tweaks to certain parts of this that produce the desired effect that we're looking for. They'll produce either an absolute maximum or an absolute minimum. And this example comes from a different source. This comes from Paul's online math notes. If you ever Google calculus problems, if you want some extra practice, his webpage is going to be one of the very first pages you see. And it is full of really great examples, really great information. Again, that's Paul's online math notes, and that's where I got this particular problem from. Let's go through the problem without further ado. Let x and y be two positive numbers such that x plus 2y is 50 and that the product of x plus 1 and x plus 2 is a maximum. So what we want to do is we want to first identify the thing we're trying to optimize, and then we want to identify the constraint. And remember that the constraint is just a set of conditions that cannot be broken. And they have a huge influence on what our maximum is in the end, what our maximum or what our minimum is in the end. And I see a bit of a typo right there. I apologize. This is actually supposed to be y minus 2, not x. This is supposed to be y plus 2, not x plus 2. I will just fix that. This is y plus 2. So let's identify the thing we're trying to optimize first. I think this last part of the question sums it up pretty well. We want to maximize this quantity right here. We want to maximize x plus 1 times y plus 2. Maximize the product of x plus 1 and y plus 2. So having this being the function that we are trying to maximize, this is our expression we want to maximize, this one must be the constraint. So if you came here from my last calculus optimization video, you remember that it involves taking the derivative. We have to create some expression, some function, take the derivative of that function, and then use that derivative to figure out information that'll lead us to find a maximized value for this expression. So when I was first taking calculus, I always had a hard time setting up the expression that we want to take the derivative of, the expression that we want to differentiate. And it's one of those things that the more you practice it, the more you understand it. Calculus is a language, kind of like algebra. We have a written representation of a problem, and we can use calculus in the same way we use algebra to create expressions that convey the same information. And it's only through that conveyance that we're able to do the optimization of a quantity. So we're trying to maximize this right here. My goal, first and foremost, is to make a function out of this information, ideally in terms of just one variable. So we see we have an x and we have a y. I want to have, I think, only x in this one. So what I want to do is I want to take y plus 2. I want to do whatever it takes to put this in terms of x, not in terms of y. And it's ultimately our constraint that helps us to do that. Whoops, did not mean to do that. So our constraint, we have x plus 2y is 50. And because I'm trying to substitute this y with something involving an x, I want to take my constraint and I want to solve for y. So we can start by subtracting both sides by x, making those go away. So once we've done that, we have 2y equals 50 minus x. And then from there, we can divide everything by 2, which yields the following. Y is negative x over 2 plus 25. So now that I have this in terms of x, I want to do just a quick substitution. I want to replace this y with this expression we know to be equivalent to y. So the quantity to be maximized would be x plus 1, that part's going to stay the same, and then we have y plus 2. So it would be negative x over 2 plus 25. And then we have a plus 2 at the end. And like I've said, I like to take expressions like this and I like to create a function out of it, use function notation. So I guess I'm just going to call it maybe p for product, maybe p of x. And the reason why I like to use a function notation is because it makes it clear what we have to do. We know that we have to take the derivative and then do something with the derivative. So it's kind of hard to conceptualize taking the derivative of something without function notation. So I just use function notation to make it clear that what we're really trying to find here is p prime of x. So before we do that though, let's do a little bit of simplifying. We have a negative x over 2 plus 25 plus 2. I want to simplify this. I want to make it just plus 27. It's always in our best interest to simplify things when possible. We're going to make this plus 27. All right, now we have a nice simplified version of our function p of x. So of course, as you might have guessed, this is a calculus video. This is a first semester calculus review of derivatives and the applications of derivatives. It might be fairly obvious that we have to take the derivative of our function. Can't do this without the derivative. Can't do this without finding p prime of x. So what we have here is we have the product rule going on. We have one linear factor being multiplied by another linear factor. So there are two ways we can do this. We can either use the product rule for derivatives, or we could maybe just do some algebraic manipulation before we take the derivative to make the process easier. It's 100% up to whoever's doing the problem. It's up to you to decide which one you're more comfortable with. But personally, I like to do the algebraic manipulation before even touching the calculus part of it. Just makes the process a lot easier and faster in the long run. So I want to maybe just FOIL this out. I want to expand this. So we're going to get negative x squared over 2 minus x over 2 plus 27x plus 27. And this is just a simplified version of p of x. So what I want to do now is take the derivative of this expression. I want to find p prime of x. So the derivative, we can just take this term by term. So the derivative of our first term is going to be negative x. The derivative of our second term is going to be negative 1/2. The derivative of our next term, derivative of 27x, is just 27. And then our last term, it's just a constant. It's a number, and a constant has a derivative of 0. We don't even really need to put that. The derivative of any number is just going to be 0. So let's clean this up a little bit. Let's maybe combine like terms while we can. So I might want to put this into improper fraction format. I want to combine these together and make it into an improper fraction just because it makes the computation a little bit easier. So I want to rewrite this. I want to make this 27 minus 1/2 minus x. And then 27 doubled is 54. So what I want to do is I want to replace 27 with 54 over 2. So now it's clear that we're going to have 53 over 2 minus x as our derivative. (53 over 2 minus x), and that's our derivative. So we've done the derivative part. We've done the part of the problem where we take the derivative. Now comes the part where we apply it. And I understand this is where a lot of people have trouble. When they're learning optimization for the first time, sometimes it isn't exactly clear what the heck we do with this derivative to help us. So just a quick refresher. I also talked about this in the last calculus optimization video. I just want to do maybe a quick refresher. Disclaimer, the function I'm about to draw is not at all related to this particular problem. This is completely random, completely arbitrary, but it helps us illustrate some of these points a little bit better. So we can tell what the maximum and minimums are going to be just by looking at a graph. We can tell that if we start from the left and move up, and start from the right and move up, eventually we're going to reach a maximum value which occurs right here. The same thing goes for traveling in the other direction. If we move from left to right, we end up here, and then if we do the same thing, if we go right to left, we can see pretty clearly that this has to be our minimum. So of course, life's peachy if we have a graph. If they give us a graph, it's really, really easy to tell what the maximums and minimums are, but we're not always going to have a graph. Sometimes they might give you some really nasty expressions that you can't graph yourself, and you may not have a graphing calculator at your disposal. So it's best not to rely on the graph to help us with this. As useful a tool as graphing is, it's best to not depend on it. It's best to learn how to use additional tools for problem solving if graphs aren't always going to be available. So we have our derivative, and the thing that the maximum and the minimum have in common is that would be the fact that they have a horizontal tangent. Maybe I'll put the picture back up. Maybe I erased it a bit prematurely. So the thing that the max and min have in common is that the derivative is going to be 0 at these 2 points. If we find the slope of the tangent line, we have a 0 derivative at the top and a 0 derivative at the bottom as well. So from a calculus viewpoint, without the graph, we just need to view this as a matter of finding the places where our derivative is 0. Identify the x values that produce p prime of x being 0. So we want to set this derivative equal to 0. And then from there, we can see that we need to add x to both sides, giving us the following. We have x equals 53 over 2. And using our specific calculus vocabulary, this is a critical point. Just a refresher on critical points. A critical point is a place where we have either a 0 derivative or something that generates odd behavior in a function, including those that produce an extraneous solution. For example, if we had, I don't know, something like this. Another critical point would be x being -3, for example, because we know we can't have a negative under a radical. Another example might be something like this, where we have a 0 in the denominator. So these are cases where it's kind of illegal, for lack of a better word, to have a negative under a radical or to have a 0 in the denominator of a fraction. So those are also included in the set of critical points. Extraneous solutions and 0 derivatives are always going to be included. So we only have one critical point right now. It is 53 over 2. So now we must make a sign chart, and it's the sign chart that will really tell us where our function is increasing and where it's decreasing. It is a chart that tells us the sign of our derivative at any particular value of x. This is our critical point, and I put a dashed line right there just to signify that the derivative is 0. It is not increasing or decreasing at this point. So now what we really want to do is determine if this interval exhibits increasing or decreasing behavior. And same thing with this interval. The way we accomplish that would be to pick any value that is less than 53 over 2 for this region. And then for the other one, we want to pick up any value that is greater than 53 over 2. So let's start with our first region. I really like 0. 0 makes things a lot easier. So I want to pick 0 as our test value. So we want to find p prime of 0, basically. We want to plug 0 into our derivative and see what we get. I'll do that up here where we have a little bit more room. P prime of 0 is 53 over 2 minus 0. So we get 53 over 2 as our answer. We don't care about the answer so much. We just care about whether it's positive or negative, and this one is indeed positive. Our derivative is greater than 0. So that means we're experiencing only increasing behavior. And I would like to do the same thing with another value. So 54 over 2 is 27, and that's just slightly higher than this. So I think I might just want to pick 27. So let's find p prime of 27. We have 53 halves minus 54 halves, which produces an answer of negative 1/2. So when x is 27, our derivative is negative. Like I said, we don't really care about the particular value. We only care about whether it's positive or negative, and in this case, it is negative. So our derivative p prime of x is strictly negative on this interval, which means that we experience only decreasing behavior on this interval. So we've already done most, if not all, of the heavy lifting. We've done the calculus. We set up an equation, we took the derivative, and we made a sign chart to identify intervals of increasing and decreasing behavior. The only thing left to do would be to find our x and our y that produce a maximum. So we already have our x. We know this is correct. We know this is the correct maximum because let's look at what this really means. Let's look at our sign chart. Let's start at the very left and let's move to the right. So we know we're increasing and increasing. Then we stop and we know we have a flat tangent line. We know we have a derivative of 0 right there. So we stop and then we decrease more and more. So this is just more than anything else a way to prove conclusively that what we have here is the answer we're looking for. This truly is a maximum. If we had it the opposite, if we had decreasing first and then increasing, something like this, that would not be a maximum but a minimum. But the fact that we're increasing and then decreasing just proves conclusively that this is what we think it is. This is indeed a maximum. Let me clear away some of the stuff we may not need anymore. So our goal now is to find y now that we know x. We want to plug x into our constraint, and only then will we be able to find the y value to go along with it. X plus 2y is 50. So what I want to do now is I want to replace x with the value that we found. And now it's just a simple matter of solving for y. So I think I'm going to double everything. So we get 53 plus 4y equals 100. And then we have 4y equals 100 minus 53, which is 47. And then y equals 47 divided by 4. All right, cool. We found our x and we found our y. So there's just one final thing we must do now. And I will show you what that is. So originally, if we trace through the problem, again, if we walk through the problem, they wanted us to maximize this quantity. So now that we know what x is and we know what y is, we can find the maximum. So I want to substitute this x with 53 over 2. I want to substitute this y with 47 over 4. And then let's find what this ends up being. So 53 over 2 is equivalent to 106 over 4. And 1 is equivalent to 4 over 4. We have 47 over 4 plus 2 over 4, which is equivalent to, or actually, sorry, this is just 2, not 2 over 4. 2 is equivalent to 8 over 4. So we have 110 over 4 times 55 over 4 and we may not even really need to put this one in terms of the denominator of 4. We might just want to revert this back to 55 over 2. For simplicity reasons. And then I'm going to use a calculator real quick. 55 times 55 is 3,225. Oh, just 3,025. My mistake. That's what I meant to say. Over 8. And then at least we can divide, I think. No, I don't think we can break this down any further. So this right here would be our maximum.